So I'll start out today with talking about joints. So a little bit more about joints. What joints are is they're just basically lines in the rock that show where it's broken apart, and how that usually happens is that one point is usually in a rock material has a lot of force pushed on it, and from that point, and from that point, uh, the amount of force will go out and then break the rock, and then it will start loading, and then it will go out again and break the rock in a different place, and then it'll load up some more force and load out and break the rock in another place. And what that usually creates is like a cascade, like a bunch of circles just kind of on top of each other of these joints. And what we see usually is just the straight lines as it propagates out. And they're from internal force, and they propagate out and they leapfrog from one to the next. So yeah, pretty much what I was talking about. And they could be due to barrel and compaction, heating and cooling, uplifts and subsidence, or folding and faulting, or landscape evolution. And joint sets are usually joints. You never really just see one joint. You'll see like a few of them, even if they're just spread out in the long distance. Depends on if you're looking at a micro or macro scale, but usually in one layer of rock you'll see a bunch of joints, or a few that are evenly spaced. Like down here you see, like in my notes I wrote that this thicker layers will have joints that are spread wider apart but still generally evenly distributed, where thinner layers will have really small even joints that are closer together. Let's see, where am I? Oh, okay, gonna go down. There's that, and here we are. So joints versus shear. It's a common mistake to mistake like a shear family for a joint family because they both have a lot of parallels within them. But you have to have a fracture to create a joint. Where like if you see like a bunch of lines on a rock, you might think like, oh well, that might be joints, but they're probably just slicken lines, which are like kind of like it looks like somebody dragged their fingers in the mud, just lightly over and over again. It was where one rock slid past another and made that surface. But most joints intersect at about 60 degrees, and a lot of times rock units that appear to be like shattered, they usually are due to jointing. It's usually due to like moving and shear. And joints are really useful in geologic terms for finding like just a bunch of different stuff like minerals, or kind of deciding where water is going to flow, in the subsurface, or just stuff like that. And we'll talk about modes of loading now, which is the tip of the line of the fracture is where a fracture meets unfractured rock and will continue as long as the loading force is larger than the tensile strength. And the tensile strength is basically like the competency of the rock again, like how well it can hold together. And if you're putting pressure on a pencil, until the amount of pressure that you're putting on that pencil exceeds the tensile strength of the pencil's not going to break. But when it does exceed it, the pencil breaks. So like there's three different main kinds, which is like the opening, which kind of like an opening of a book. Like as you spread it apart, it just kind of propagates in and goes further. A normal shear, which just kind of propagates and shears, and then one that is like a scissor, which kind of rotates on like an axis kind of, and then kind of goes like this. Mm-hmm. There's some more descriptors in there. This image is really useful, actually. I actually use this quite a bit to kind of think about joints and fractures and things like that. What this is basically like a good cartoon representative of like a fracture zone, which has these right here, which are the ribs, and these right here, which are the plumes. And so, like, as the plumes go out, they kind of tell you the direction that the fault is going, and the ribs happen like as you know, like when something goes, and then waits and needs to load, and then waits and needs to load, waits and needs to load. That's where the ribs are forming. So up here you have these plumes, these hackle fringes up here, which are just as a fault goes out, you know, it takes a lot of energy to drive through solid rock. It takes a lot of energy to drive through solid rock, and as it goes out, you know, it drives, and then it starts losing its energy and kind of spreads out and stops. And that's what those hackle fringes are, is like the edges of where the energy is, and that's where it's like dissipating. So like if you find a lot of hackle fringes, you're near like the edge of a faulted zone. But yeah, and then of course, like over here is like the origin, and there's a few other things that are pretty cool in here, like echelon segments, which are just basically like echelon means like in rows, which segments that are in rows. But yeah, so like I said, you know, like this is an ideal joint face. The plumes propagate from the origin. The ribs are a slight change where the propagation allowed, and the fringe is located where, yeah. Like how I'm doing this is like I'm kind of reading the notebook as I go along, and I'm describing things as I see them, you know, to kind of also test myself to see how much I know, and I'll go back and watch the videos and restudy where I'm a little bit foggy on. But so far I've been doing pretty okay for me, I think. So like, yeah, this is talking about like in granite, like how I think it's joints, right? Yeah, how joints go out is usually in circles, and then they'll start to kind of ellipsoid out, and this is just a different kind of jointing system where like the origin is like right here, and it's like pluming out, and then, you know, like these little hackle fringes and stuff on the top, you know, would be up here in this area. So okay, yeah, here's some, it's just some more in-depth stuff about like the plumes and fringes, so, or the plumes and ribs. So like these are the plumes, and it shows direction. So the fault started here, and it's propagating out, and these kind of like point into where the direction is, and the ribs, they just uh, the relation of the ribs, like as they expand out, so like they'll be huge further away, and then they'll kind of condense down towards the origin. But usually in sedimentary rock, these things happen from like some kind of inconsistency in the rock, like a fossil or something, some kind of a weakness that where there's a lot of force in one area, and then it's just pushing on the entire area, and there's one weak spot, and then that will cause the break. Down here, there's some more, you know, like where this opening is, you know, just showing like how the plumes go, and then like a new plume starts, and this is where the energy kind of dissipates. That's when the new ribs form, and then a new plume starts, ribs, plumes. Kind of the same thing right here, just at an angle. And usually it's like more like this. This is kind of a perfect example, which is difficult to find in the field, but you'll find stuff more like this. Yep, tend to concentrate around the origin, perpendicular plumes. The main joint face of the plume is opposite to that of the ribs, represent the joint face. Travels along its axis. Oh yeah, like this is like the joint's axis, and like the hackle fringes that come out of it, right? Yeah, like the tip to tip, you know, like they'll join, and you can kind of follow a fault like that. And right here is a kink and a hook, you know, like it's kind of like the shape kink hook. Geology is usually pretty self-explanatory. Let's see. joints occupy the fin. Gradual twist. Yep. Abrupt twist. Yep. Yep. So this is basically just saying like just different kinds, like how you'll kind of see them in the field. But let's see. Oh, here's some more columnar jointing, which is as the basaltic lava cools, it doesn't just cool like to make that shape, it also cools up and down, so it creates like cake layers, and that's a good way of like kind of, I don't know, when you see them, the columnar joints are pretty obvious, but sometimes like I just went out in the field the other day and we saw some that were difficult to tell that they were columnar joints, and you had to really see, you had to kind of get closer and look at the surface from a different angle to see the like 120 degree corners that they have, like these right here. They have little 120 degree corners, and you had to really get close to see, like you only saw like this in one section, and then maybe you saw another one facing in a different direction, but you could tell that that was a basaltic columnar joint because of just those little details. Oh, I should probably flip my page and read. But yep, and like this is just basically saying like each bed has its own origin. Like just because you find one origin doesn't mean you'll find it in the same area in the next. They can be on the opposite. They can share origins, like right in that contact. That could be a zone of weakness, or like here where this layer is a shale layer. All of the origins are kind of lined up in a row along each other. And I think that's it down here. It's just saying like that since I can just move my face. There, you can read all that. There, you can read all that. Okay, well, I think that's it for this first section. Next, we'll be going over like some more intense structural stuff. This like all the way up until here was just kind of the basics, and then it gets like into some more in-depth stuff. So yeah, next time.